Today, we're going to explore a really fascinating partnership. What happens when the classical computer, the one you're used to, teams up with the absolutely mind-bending power of a quantum processor? Well, it turns out it's a collaboration that's already solving problems we once thought were, well, pretty much impossible. Okay, so think about the last thing you ordered online. Seems so simple, right? You click a button, and a few days later, poof, it's right there at your doorstep. But behind that one simple click, oh man, there's a logistics puzzle of just staggering complexity. We're talking a massive web of warehouses, trucks, and literally millions of possible routes. And the scale of this puzzle, it's hard to even wrap your head around. The global logistics market is a $2.5 trillion industry. Yeah, trillion with a T. So solving this puzzle isn't just about, getting your package a little faster. Getting it even a tiny bit more efficient has absolutely massive economic consequences. But here's the catch. As our supply chains get more and more complex, we are starting to hit a wall, a really big one. Even our most powerful, room-sized classical supercomputers, they're beginning to struggle with the sheer, overwhelming scale of these optimization challenges. So why is that? Well, it's because logistics planning is what's known as an NP-hard problem. Now, that sounds super technical, but in simple terms, just think of it like this. For every single new stop you add to a delivery route, the number of possible paths doesn't just go up, it explodes exponentially. It gets so big so fast that you very quickly reach a point where even the world's fastest supercomputer would literally need centuries to check every single option. It's just not practical. And this is what really illustrates the stakes here. We don't even need a perfect 100% solution. In a market this massive, just a tiny 1% improvement in efficiency, saving a little bit of fuel here, a little bit of time there, that can unlock billions of dollars in value. The incentive to crack this thing is it's huge. So, if our classical computers are hitting this wall, what's the answer? Well, a lot of people believe it's quantum computing. But here's the thing about today's quantum machines. They come with their own really unique set of incredible promises and some pretty serious limitations. The fundamental difference, it all comes down to how they process information. A classical computer bit, right, is basically like a light switch. It's either on or it's off, a 1 or a 0, simple. But a quantum bit, or a qubit, is way more like a dimmer switch. It can be on, it can be off, or it can be any shade in between, all at the exact same time. This wild property is called superposition, and it's the secret sauce that lets a quantum computer explore this vast landscape of possibilities all at once. And this is exactly where we are right now. Back in 2018, the physicist John Preskill just perfectly captured the current state of the art with this one term, the NISQ era. And trust me, it's a really critical concept for understanding exactly where we stand today. So what does NISQ actually mean? Let's break it down. The N stands for noisy, I is for intermediate scale, and Q, of course, is for quantum. So intermediate scale just means we're talking about processors with, say, 50 to a few thousand qubits, not the millions we'll need eventually. But the most important word in that whole acronym, by far, is noisy. See, quantum states are unbelievably fragile. The slightest vibration, the tiniest temperature change can just knock them off course, creating what we call noise that leads to errors in the calculations. And that right there brings us to the core dilemma of our time. These NISQ computers, they have absolutely incredible potential, but they're too small and they're way too error-prone to tackle these huge real-world problems all by themselves. They're powerful, but they just can't go it alone. They need a partner. And get this, that partner, it's the very classical computer it was supposedly meant to replace. Isn't that great? And this brings us to what's called the hybrid model. It's this really elegant approach that says, hey, let's not wait for perfect quantum machines. Instead, it creates a powerful partnership between both systems, right here, right now. The central idea is actually really simple. It's just a division of labor. You play to your strengths, you give the tasks that classical computers are amazing at, like crunching huge data sets and running standard algorithms. You give that to the classical machine. And then you assign the really tricky tasks, the ones that require exploring a massive number of possibilities, to the quantum processor. And it works as this really cool feedback loop. Think of it like a conversation. First, you've got the classical strategist, setting up the problem, defining all the parameters. Then, step 2, it hands that problem over to the quantum explorer, which dives into that huge landscape of potential solutions. Step 3, The quantum insights are measured and sent back to the classical computer. And then finally, step 4, the classical optimizer takes that feedback and refines the parameters. And then you just repeat. The dialogue keeps going, with each loop getting you closer and closer to the best possible answer. And this is so cool because this isn't just theory. Researchers recently put this exact hybrid model to the test in a real-world, honest-to-goodness scenario, optimizing last-mile delivery. You know, that final and by far most complex step in getting a package from the warehouse to your front door. So here's what they did. They broke the problem down into 2 main parts. First, there's clustering, basically grouping nearby customers together in a smart way. And then second, there's routing, finding the absolute shortest path to deliver to everyone within each of those groups. And for both of these tasks, they created a classical algorithm and a quantum one to have a head-to-head competition to see which one performed best. And the results were, honestly, fascinating. When it came to that first task, the clustering part, the quantum algorithm was the clear winner. No contest, especially when they fed it messy, randomly distributed data, the kind of chaotic data you actually find in the real world. So why was it better? Well, the quantum processor's unique ability to see that whole landscape of possibilities at once allowed it to find much smarter groupings. It found these hidden patterns in the chaos that the classical algorithm just completely missed. This is a perfect textbook example of a real quantum advantage right here. But, and you have to hear this part because it's just as important, for the second task, actually finding the shortest route, the classical algorithm was still the winner. Google's highly optimized OR tools, which have been refined for years, produced much more efficient routes than the noisy quantum processor could manage. And that is the crucial point right there. This perfectly demonstrates the power of the hybrid approach. It's not about quantum versus classical. It's not a fight. It's about being smart. It's about teamwork. You use the quantum processor for the one specific messy task that it's amazing at, the clustering, and you let the reliable classical workhorse handle the rest. Best tool for the job. So let's look ahead. This hybrid model is clearly our best strategy for the NISQ era, for right now. But what comes next? I mean, what's on the horizon after these noisy intermediate scale machines? Well, the field's major players have all published these really ambitious roadmaps. You've got giants like IBM and Quantinuum who are literally in a race to deliver the first fault-tolerant systems before the end of this decade. And while sure, some analysts think widespread applications might be a few years after that, one thing is absolutely clear. The pace of progress is just accelerating like crazy. And let me tell you, fault-tolerant is the ultimate game changer. This means scaling up from thousands of those noisy qubits to tens of thousands of stable, constantly error-corrected ones. We're talking about machines with enough raw power to run legendary code like Shor's algorithm, which, is the one that could theoretically crack the very encryption that protects our entire digital world today. It's a huge deal. But here's the beautiful part. We don't have to wait for that future to start innovating. The hybrid system is that crucial stepping stone. It's the bridge. It's a practical, really intelligent way to start extracting real value from the powerful, yes, but still imperfect quantum computers we have right now. So that leaves us with one final and I think pretty provocative question. As we cross that bridge from today's hybrid systems to that fully fault-tolerant future, when these incredible machines finally unlock their true potential, which of the world's so-called unsolvable problems, we're talking everything from discovering new medicines to tackling climate science, which ones should we point them at first?